Welcome back. We are continuing our discussion of SDN in the wild, and in particular in this lesson we will focus on wide area backbone networks. We will start by looking at what is called a software-defined internet exchange. Before we get into discussing the advantages of deploying SDN in an internet exchange, let's first understand better the limitations of the Border Gateway Protocol, which is the Internet's current interdomain routing protocol. One limitation is that routing can only occur on destination IP prefix. In particular, there is no customization of routes by application, sender, and so forth. This makes it particularly difficult to send traffic along custom routes for particular applications such as video streaming or other types of applications that might want particular performance guarantees. Another limitation of BGP is that an autonomous system or a network can only influence routing for immediate neighbors. An AS has no ability to affect the end-to-end path that traffic might take from source to destination. Finally, operators can only express policy indirectly. There are only indirect mechanisms to influence path selection, such as local preference or AS path prepending. There is simply no way to say that you would like a particular traffic flow to traverse a particular set of routers or a particular set of ASs. The operator must rely entirely on indirect mechanisms. So if we'd like to evolve the Border Gateway Protocol to support a wider variety of applications, one idea is to evolve the interdomain routing protocol at the internet exchanges. An internet exchange is a particularly attractive place to deploy new routing technology, since deploying new technology at a single internet exchange can yield benefits for tens or hundreds of internet service providers that connect at that exchange. IXPs right now are also currently experiencing a rebirth and wanting to differentiate themselves from one another. So they're looking for new technologies to make them a more attractive place for ISPs to come and interconnect. SDN is one way that one IXP might differentiate itself from another. Finally, new traffic demands and new applications, such as video streaming, create the need for much richer peering arrangements and much more sophisticated business relationships than exist in today's internet routing ecosystem. Deploying SDN at an internet exchange involves many opportunities and challenges. As far as opportunities are concerned, deploying SDN at the exchange offers freedom from the constraints of having to work within today's internet protocols. SDN allows switches to forward based on a variety of different packet header fields. Switches can be controlled from remote networks as opposed to just the immediate neighbors. And the controller has direct control over the data plane. So SDN controllers can affect traffic in much more direct ways than today's indirect mechanisms. Unfortunately, there are also challenges to deploying SDN in an internet exchange. There is no existing SDN control framework for interdomain routing, and even if there were, deploying such a control framework poses significant scaling challenges, since that controller would have to handle routing for hundreds to thousands of ISPs that connect at the internet exchange point. Today's IXPs cannot support many different functions that might be attractive to network operators. For example, it's not possible for ASs to engage in application-specific peering or peering for specific types of applications. It wouldn't be possible, for example, for Netflix to peer with Comcast, but only for video streaming traffic. Peering today is all or nothing. It is also particularly hard to redirect specific subsets of traffic to middle boxes that might perform more complex operations on traffic, such as transcoding or encryption. Traffic offloading is also difficult. Supposing that there are 3 ISPs that all connect at the same exchange point, and one of those ISPs is an intermediate transit provider for the other 2. In today's IXP, traffic must traverse the links of the intermediate ISP that's providing transit between the other 2, consuming valuable bandwidth on the ingoing and outgoing links at the exchange for that intermediate ISP. It is also somewhat difficult for an autonomous system to drop inbound traffic that's not associated with any peering relationship. Finally, it's difficult to rewrite a destination IP address for the purposes of load balancing. Today, content providers perform load balancing using the domain name system. So, for example, if you look up a domain name like google.com, you might get a different IP address when you look that domain name up at one point or another point. This, again, is a fairly indirect mechanism for performing load balancing. A more direct mechanism would be to rewrite the destination IP address, but this is particularly tricky using today's infrastructure. An initial design of a software-defined internet exchange, or an SDX, might look as follows. A controller might control one or more switches at the exchange where ISPs interconnect with one another. That controller would take as input routes per IP prefix, potentially including also other attributes, such as price or performance. The controller could also take as input a selection function that is specific for that particular AS. This stands in contrast to BGP today, where all ASs perform the same default route selection function. The outputs of the controller computation are fib entries in the switch, or one or more entries per AS that satisfy the selection criteria for that AS. The controller might also specify rules that rewrite packet headers. For example, the controller might specify that the destination IP address for certain flows should be rewritten for the purposes of, say, load balancing. In summary, the SDX operation has two steps. In the first step, the controller receives routes and auxiliary information, and in the second step, each participant at the exchange submits a function to the controller, which executes to select the routes, rewrite packets, and so forth. The controller then ultimately pushes those rules to one or more physical switches that sit at the exchange. The implementation of the SDX architecture is as follows. The runtime for SDX sits on top of Pyretic. On top of the runtime are applications that individual ASs write that specify policies. Note that an AS need not be physically present at the exchange to be running an application. So, for example, ASD might write an application that controls remote forwarding behavior. This might be useful, for example, in the case of a content provider that wishes to control forwarding along the path closer to its customers. Each AS sees only its own virtual IXP topology, thus providing isolation and preventing an AS from writing an application that interferes with other AS's policies. Those applications run on top of the SDX runtime, and the runtime makes decisions based on both the participants' applications, policies, and auxiliary information, such as that which it might receive from a route server, the resource public key infrastructure indicating ownership of prefixes, and so forth. The runtime then resolves conflicts using parallel and sequential composition from Pyretic. Let's take a closer look at the virtual SDX abstraction that each AS sees. ISPs that do not have business relationships with one another simply cannot see each other in their virtual SDX. For example, in the picture shown here, suppose that ASA and ASC do not have a business relationship. In this case, ASA does not see ASC in its virtual SDX topology. Similarly, ASC does not see ASA in its virtual IXP topology. This isolation is enforced using symbolic execution at the SDX. Symbolic execution tags packets on input and uses a state machine to determine the appropriate physical output port for that packet. For example, if a packet arrives on A's ingress port, the finite state machine looks at the destination IP address for that packet. Suppose that the destination IP address is IPB. That packet would then transition to the virtual state signifying switch B, which would then apply the next state transition to pass that packet to the state representing the physical egress port for ASB. This state machine abstraction prevents packets from taking paths that are not compliant with the policies of the AS at the exchange. Once the appropriate paths and policies have been computed, the SDX runtime composes the AS's policies in the order of packet traversal based on the result from the symbolic execution. For example, a packet that arrives on ASA's ingress port that is destined for IP B would be subject to A's policies followed by B's policies. Here is an example of a topology where three ASs connect at the software-defined Internet exchange. ASs A and C do not have a business relationship with one another, so must use ASB for transit. But we do not want the traffic between A and C to pass through B's ingress and egress links. At the SDX, we run a traffic offloading application that ensures that traffic between A and C only pass through the physical switch at the exchange, even though logically B is the transit provider. You can see here that the ASs are able to ping one another. We have included the code for this example on the course website. In summary, interdomain routing continues to be plagued by problems with security, manageability, troubleshooting, and so forth. An SDN-based Internet exchange is promising because it can fix these problems and present new opportunities for applications that are simply not possible within the constraints of today's interdomain routing protocols. Many research challenges remain both for building this exchange and for using it, but there is already a preliminary implementation which we have pointed you to in the course resources, and you are welcome to have a look at.